Thank you so much. So I will be talking about a recent modeling effort to look at the effects of both solar evolution and the lunar paleomagnetic effects on the lunar argon-argon antiquity indicator. So first off, what is the antiquity indicator? So the antiquity indicator is actually a semi-empirical method of dating the age at which a certain or a given lunar sample was exposed to the solar wind. And the way in which this is done is by looking at the ratio of two different trapped noble gas isotopes, 40 argon and 36 argon, that are naturally found in returned lunar samples. And the figure I showed here is sort of a compilation from an Oixer et al. 2001 figure, which plots the inferred sample exposure age on the x-axis versus this ratio of 40 argon over 36 argon for a number of different lunar samples. And the way to interpret this plot is that the youngest samples, those samples that were exposed to the solar wind in very recent times, geologically speaking, tend to have lower ratios of 40 over 36 argon. Whereas very old samples, those samples that were exposed to the solar wind several billion years ago, tend to have much higher 40 argon over 36 argon ratios. What you also see on this plot, you see that the solid black line is sort of just an empirical curve that's drawn to fit the data. The dashed curve, it's worth noting, and as I'll talk in a couple slides, is actually the radioactive decay rate of potassium-40 inside the moon to argon-40. And you see to first order, they kind of roughly match, and it indicates that this argon-40 is likely coming from the internal decay of potassium-40 in the moon. So in reality, how does we think this antiquity indicator works? So we need two ingredients. We need argon-36 and argon-40. Argon-36 only comes from the sun. The only source of this isotope is actually the solar wind itself. It's a minor ion in the solar wind. And so over billions of years, this argon-36 is continually irradiating the surface of the moon and implanting argon-36 into the soil. One important assumption this makes is that this flux of 36 argon, or the flux of the solar wind in total, is constant over geologic time. And we'll get back to this about whether or not that's actually true. The other half of the equation is 40 argon. So the best hypothesis for where 40 argon comes from is actually the radioactive decay of primordial 40 potassium, which is locked inside the moon. The radioactive decay half-life of 40 potassium is about 1.25 billion years. That was this curve, this dashed curve you saw in the previous plot. After the potassium decays into 40 argon, the 40 argon is relatively inert. It outgasses to the lunar crust. It forms the well-known argon exosphere at the moon. It's eventually reionized either by photoionization or electron impact ionization and driven back down into the soil. So you have these two competing different sources of 36 argon on one hand, 40 argon on the other, and the ratio of these two is generally what we're looking at in this antiquity indicator. And the assumptions is that the solar wind flux stays constant over time, and the 40 argon flux follows this radioactive decay curve. But there's been recent work that suggested or really definitively shown that the moon possessed a paleomagnetic field for a very large fraction of its lifetime. The figure that you see on the left is sort of a summary plot from Mihani et al. 2020 that's looking at the inferred strength of the paleodynamo over the moon's lifetime. So in the far left of this plot, about 4 billion years ago, the moon had a very strong dynamo, as strong as the Earth's dynamo field at the surface. There's this intermediate region from about 3 to 1 billion years before the present, where the moon is inferred to have about a 5 microtesla field. To put it in context, that's about 10 times the strength of Mercury's present-day field, so that is a very strong field. And then finally, within the last billion years or so, evidence suggests that the dynamo eventually shut off. But the question then becomes, if the moon had a paleomagnetosphere for on the order of 2/3 or 3/4 of its lifetime, would that have sort of quote unquote broken our understanding of how the various argon-36 and argon-40 make it down to the surface and allow this antiquity indicator to work? So how is this ratio actually coming to work that we see in the lunar samples? The figure on the right shows just an example from some previous simulations our group did a couple years back looking at what the effects of including a paleodynamo and the moon's interaction with the solar wind would be. You see the magnetic field and the solar wind density figures. So very obvious evidence that the moon would have a strong paleomagnetosphere that would strongly divert the solar wind before it gets down to the surface. So in order to test this idea of what is the paleomagnetosphere doing to both the argon-36 and the argon-40 fluxes, we undertook a series of numerical simulations to slowly turn up the paleomagnetic field strength and look at both the incoming solar wind 36 argon flux and then the ionization of argon-40 coming from degassing of the lunar interior. The results that you show here are for the flux of solar wind 36 argon down to the lunar surface. So to orient you, the moon is obviously in the middle. The solar wind flux is flowing from right to left. And the 4 panels that I show on the far left are the 0 nanotesla case that's sort of representative of the moon today with no paleomagnetic field. And then I slowly increase the field strength from 250 nanotesla, 1 microtesla, and then 4 microtesla. And the 4 microtesla case is closest to sort of this intermediate period of the moon's dynamo. That's really what we think the moon had for about 1.5 to 2 billion years of its lifetime. What you see here in the colors are the flux of argon-36, and you can see very obviously that as we increase the strength of the dynamo in the moon, we drastically alter the flux of argon-36 to the moon. To first order, the moon is actually shielded over much of its surface, similar to how the Earth is itself shielded from the solar wind by the Earth's own dynamo field. It's generally well understood how that works. We do see evidence of some precipitation of argon-36 down through the cusps. So these are the magnetic polar regions. That's actually a process that's very similar to how the aurora work at Earth, except here at the moon, we're talking about irradiation of the surface itself. You also see there's some evidence of trapped particles, especially in the largermost simulations. So you can get solar wind ions that are trapped within the magnetosphere itself and precipitate down to the surface. So the presence of a paleomagnetosphere definitely alters the flux of solar wind 36 argon. We also ionized argon-40 from the lunar exosphere itself. And we do the same series of strengths of the paleomagnetosphere. You see on the left is sort of the case today where we're picking up ions into the solar wind with sort of a classical cycloidal trajectory. But as soon as we start to turn on the paleomagnetic field, you start to see that the fluxes are suppressed. They're actually contained more within the paleomagnetosphere itself, and you're actually increasing the amount of recycling of argon-40, and you're altering the rates at which these ions are implanted down into the surface. If we sort of average over the lunar surface, what the total flux is for both argon-36 and argon-40 as a function of the paleomagnetic field strength, we can see in the top panel that for the argon-36 relative to what it is for a lack of any paleomagnetic fields, we go all the way out to the 4,000 nanotesla case, which is the presumed case for the moon. We see that actually the paleomagnetic fields can suppress the argon-36 flux by about a factor of 10. So even though some flux is getting in through the cusps or in the radiation belts, overall it's only 10% of the undisturbed flux. In contrast, we see that the argon-40, which is starting within the paleomagnetic sphere from the lunar exosphere and being ionized, actually is increased by about a factor of 2 or 3. So on one hand, we're holding off a bunch of the argon-36 from the sun, and we're retaining a little bit more of the argon-40 from the lunar exosphere itself. And that might actually affect how this calibration might work in terms of the ratio of argon-40 to argon-36. So in conclusion, these results have shown that the presence of a paleomagnetosphere is definitely something that alters the flux of both solar wind argon-36 and lunar exospheric argon-40 to the lunar soil. It's definitely something that has to be taken into account if we really want to understand how the Antiquity indicator works. It actually suggests that this ratio that we see in the data, even though to first order it matches the radioactive decay curve of 40 potassium into 40 argon, the picture is actually more complicated than that. It's not fully directly related just to the 40 potassium decay rate. And another piece of the puzzle that we've just started thinking about as well is that actually the flux of solar wind from the sun has likely dropped by a factor of at least 3, if not a factor of 10 over the sun's lifetime. So when the sun was much younger, it had a much more intense solar wind flux than it does today. And so even the bulk 36 argon flux is changing over time. So these are all components of the picture of how do we actually understand how this antiquity indicator works in the presence of a paleomagnetosphere. And we've really just started to explore this. So at that point, I will stop and take questions. Thanks.
Are there any questions for Andrew in the room? Yes, we have.
Hey, Brett Denemi, APL. Wow, I'm too tall for this. Sorry. Okay, this is really cool work. Thank you for sharing. I'm also curious if this could then shed light on kind of the paleomagnetosphere controversy. If you do see this correlation, then maybe that would suggest the magnetosphere was not as strong in the past or something.
Yeah, it's definitely something I've scratched my head about, because on one hand, the correlation, this figure you show on the right, looks pretty good to first order. And then you kind of introduce the paleomagnetosphere and they say, it's completely broken. But in fact, somehow it still seems to roughly match the 40 potassium decay rate. One of the challenges, I think, is actually if if you look back at these figures, the precipitation of some of these ions under the surface is actually very inhomogeneous across the lunar surface. And the fact that all of the samples that we actually have roughly come from the near side in roughly equatorial regions could potentially be biasing our understanding of this. If we were able to get samples from the polar regions where maybe the ratio of the fluxes were different, and we compared what the argon-argon antiquity indicator was versus other methods of dating the samples, we might show more spread in the data, which I think would actually argue that this paleomagnetosphere did exist. So a little bit of is I think limited by sample bias that we have, but it is an interesting conundrum that it seems to first order to work without the need for a paleomagnetosphere, but there's a lot of other evidence that does suggest that there is a paleomagnetosphere, and thus you can't really ignore these effects at some degree.
Thank you. So Artemis samples will be our rescue.
Yes, please.
As many as we can get.
Yes.
Thank you very much, Andrew.